Okay, so we're going to problem solve with sinusoidal derivatives, which is essentially trigonometric equations, right? And we're going to find the derivatives of them. So we have a problem that's given to us here. Power supply delivers a voltage signal that consists of an alternating current, and that's usually written as AC in electricity, and as a direct current, which is usually written as DC component. Where T is time in seconds, and the voltage is represented at V at T, so the voltage with respect to T is 5T, and this is supposed to be sine T being our variable plus 12. What are the maximum voltages, and what times do occur? Okay, so there are kind of two ways we can go about this. We can go about this if we know anything about sinusoidal functions and how to transform them. We can get a pretty good idea where these max and mins are going to be, okay? And we'll rewrite this out here, but we can prove it using our calculus here. Since voltage in time is equal to 5 times sine, and t is kind of x plus 12. Well, if you recall transforming functions, this is considered like an a variable, and this is, they use different letters. I think they call it c normally, but essentially what this is vertical translations. Okay, and A has to do with vertical stretches, compressions, and reflections. Okay, and these are what these two things do. All the other, there are no other variables technically affecting this. So if you know how a normal sinusoidal function works, okay, we know that it has a max at 1 and a minimum at -1. Okay, and at 90 or at pi over 2, working in radians, we read a max value. We hit our equation of the axis, or the middle of the sinusoidal function, again at pi. At 3 pi over 2, we're at our -1, so that's our minimum. And then back at 2 pi, or 360 degrees, is when our entire period occurs. Okay? Now, since this t hasn't been affected horizontally, the period is still going to be the same. The period is still our 2 pi. There's been a vertical translation up 12. So in other words, you take the equation of the axis and you move it up 12. So in other words, we kind of, without our vertical stretch yet, we have a peak of 13 and a minimum of 11, because 12 is right in the middle of those two. Okay, and I know I could show you on a graph, and we'll do it in a sec. We also have a stretch of 5. In other words, our zeros will all stay the same, but we multiply all of our major y values by the factor of 5. So 0 times 5 still gives us 0. But this 1 now goes all the way up to the number 5, and the minimum goes all the way down to -5. So in other words, there's an amplitude, okay, of 5. In other words, it goes 5 up from the equation of the axis and 5 down. Well, we just stated how our new equation of the axis is at the number 12. So if we go 5 up from there, we have a max at 17 and a min at, we subtract 5. So that would give us, I'm drawing a blank, 7. Great. 17 and 7. So those are going to be our max and our min. But we want to kind of prove these without just relying on our transforming function. So we kind of have an idea of where our answer should be. We also know that a max and a min should occur when a line tangent to the curve would be 0. And we know if we derive a function, we are essentially be able to find the slopes of this curved line. If we set it equal to 0, then we'll be able to find out our exact max and min values. So if we go to derive this function, v prime t, okay, if we go to derive this, our first one you can think of like a product. So we have 5 times sine t plus 12. Okay. So if we're going to do this, think of it like this. If we were to derive our first value 5 would end up being 0. So 0 times anything eliminates it. Then we find the derivative of our sine. Well, what is our derivative of our sine? Do you recall?
Cos?
Yeah, it's going to be cos, okay? So we end up at cos t, okay? And derivative of 12 is essentially 0. We could write in plus 0, but it's really irrelevant. So our derivative of this function is 5 cos t. Does that make sense and stuff? Okay, great. So we know that to find a tangent of the curve, we want to set it equal to 0. Okay, so we're going to set 0 is equal to 5 cos t. Okay, and the goal is to essentially just isolate for our value of t. So we bring 5 over to the other side, and when we do that, we divide. 0 divided by 5 still gives us 0. So 0 equals cos t. So we're looking for when cos is equal to 0. And there's no parameters on this. So there's actually many times when cos is equal to 0. Okay, and our cos function, okay, and I'm going to draw that out again. So it does help to have an idea of our sinusoidal functions. If you recall our cos function, it also has a max at 1. And it actually hits 0 at pi over 2. Has a minimum of -1 at pi. Okay, so it kind of does this type of curve. And it comes back up at 3 pi over 2, which is another 0. And then it has another maximum at 2 pi. Okay? So these values here are when we're at 0. Okay? And it's kind of repeating this pattern as we go through it. We have a value of pi over 2. Okay? We have another value at 3 pi over 2. And essentially this idea is we're constantly adding, okay? We're adding what would be considered pi. We're having a rotation of every pi, we're hitting a max or a min. So we would add pi again to this, and we'd be left at 5 pi over 2. If we added pi again, we'd have 7 pi over 2. Is this making sense? Mm-hmm. Yeah. And then if we were to go backwards, we essentially subtract by pi, okay? And then that would give us negative pi over 2, and then negative 3 pi over 2. And it's almost symmetrical, essentially, these values. So we subtract pi again. So these go to technically infinity to the left and technically infinity to the right. So these are all specific values here. And these are when cos is equal to 0. But what it's telling us is that's when we're reaching our max and minimum values. Okay? So what this is saying is I should be able to plug in any one of these numbers into our original equation, and our original equation was our 5 sine t plus 12. And when we plug it in, we should find out what those max and min values are. Now, by looking at the cos function, we can get an idea that one of them is going to be like a rising action and another one's a falling action. So in other words, one of these is going to be a max and one's going to be a min. We just don't know which is going to be which. So we'll test these out and to see if we kind of get an alternating idea here. So we have our voltage at, and I guess we'll start with pi over 2, is equal to 5 sine, this is our t, so pi over 2 plus 12. Okay. Now, sine pi over 2. Do you happen to know what that is off the top of your head? Sine, it's considered 1. Technically, yes. And it's the idea of sine 90, right? So we drew it over here. It's technically our value of 1. So we have 5 times 1 plus 12. Well, that's going to give us 5 plus 12 is 17. And we already assumed that was one of them. Let's go with our next value here. Voltage at 3 pi over 2 equals 5 sine 3 pi over 2 plus 12. We'll squeeze it in there. Okay. Sine 3 pi over 2.
Negative 1?
Yeah, we get negative 1 plus 12. So we get negative 5 plus 12. And how much faster at it now? We have our value of 7. So essentially, we can kind of deduce that these will be our max values, and these will be our minimum values. And because it's sinusoidal, we can kind of keep this pattern as we go through. Max, min, max, min. This will be a minimum. This will be a maximum. So our values, our domain, or all of these are times when we're reaching a max or a minimum value, and our max and min values are alternating between the number 17 and 7. Okay? Okay, so we need to build an equation for set notation, and we know that essentially our first value was our pi 2, and really we could kind of build this with anything. But the idea is that our pi 2, and we're adding, like we said, pi. We're going up in a sequential order, and we're constantly going up by 1 pi. So you could kind of say if this was like our starting point, we go up by 1 pi, then we go up for our next number from the starting point, well, we go up 2 pi. And then from the starting point to get to our next number, we go by 3 pi, and then 4 pi, 5, 6. So in other words, we're increasing our values by integers. We're going up by whole numbers only. We're not going up by like 1.5 because that would fall somewhere in here, and that's not a max or a min value. That's somewhere in this idea, okay? So we're going to build an equation out of this. Our starting point, like we said, was our pi over 2, okay? And we're going to constantly be adding a variable, we'll call it variable I in this case for integers, plus pi. Okay, so we're substituting in 1 pi or 2 pi or 3 pi or 4 pi or 5 pi for the value of I, and the pi is always staying the same. Now, one of the ways you can build this equation here is you can actually common factor and make this maybe a little more straightforward, because we know that pi over 2 is our starting point. If we were to common factor out pi over 2 and pi over 2, okay, well, the first number here, pi over 2 divided by pi over 2, will give us a value of 1, okay? So my pi over 2 comes to the outside, and we have 1 plus, okay? And maybe I'll go over fraction division very quickly. If I have I pi divided by pi over 2, it's the same thing as multiplying by 2 over pi, okay? And this would be over 1. Well, when I do that, my pi's kind of cancel out. Anything over 1 is just that number, right? So it's 2 times I. So in other words, plus 2I. Is that what they built here? Yeah, that's essentially what they built here. So this formula is setting us up for no matter what integer we put in, okay, so whether it's the first one, we multiply these values by our pi over 2, and it'll give us our new number. So if we want to figure out one, I guess the best word would be deviation or movement from our original, we plug in the number 1. Well, that's 2 plus 1 is 3. 3 times pi is 3 pi over 2, which is exactly our first number in this direction. If we were to do 2, go back down. 2 by 2 is 4, plus 1 is 5. That gives us 5 pi over 2, and that's the next number in our sequence. As set notation, let's see if I can remember how that was this set notation. They have it here. They've written it as time is subject to this equation, and the equation being that time is equal to what we've got, pi over 2, 1 plus 2i, such that I is every, and they use the letter Z. Usually they actually use I, from my experience in math, to represent integers. You might use the letter Z, but it's essentially I is every real integer. So what we're saying is this number here, because technically it's a variable, it could be anything. It's an infinite number of solutions. A lot of times when you write set notation, you write R, and R represents every real number. That would be everything. But in our case, we can only work with integer numbers, which are whole numbers that are positive or negative. So like positive 1, positive 2, negative 1, negative 2. So that's what this kind of set notation is setting up for us for all of our max and min values.